So in chapter 13, we looked at bodies in motion due to an unbalanced external force acting on that body. A body in motion possesses energy, receiving it from a force acting on a body through a distance. And this is what we call work. So work is due to an applied force acting over a distance. In other words, we write this out in equation form. We have work is equal to force times distance. And if we were to give each of these symbols, typically as you'll see in the textbook, work, also known as U, large U, capital U, instead of W, because normally we see that as weight, is equal to capital F times distance, or what we've typically called displacement. In terms of units, work is in the form of joules, whereas the other terms are newtons and meters. So that tells us obviously that 1 joule is equal to 1 Newton meter. Similarly, if we're looking at using US customary units, a joule in US customary units is typically referred to as foot-pounds, and that would make sense since our think of weight, for example, a force is in terms of pounds, and our distance in terms of feet. Now, what does this really mean from an actual, real world life example? Well, let's take a look at a box again. So we have a box that is sitting on the ground, and it has mass m. We are going to apply a force as we've done before. So we know we apply a force in that direction, an external unbalance force. We're going to get an acceleration in that same direction. So we can show that here. A. We're going to move this box, and this box is going to move a certain distance. So same box, no change in mass. However, we do have a change in its position. So that is shown here as S. So again, a force acting on this mass displaces this mass a certain distance. So force times that distance gives us the total work involved in moving that block. There's a couple of really important notes I want to write down here. So I'm going to add in a page. What I really want you to understand here is the following. So some important notes. The first is that the force must be in the same direction as distance. So force must be in same direction as distance. So just as we've seen in multiple chapters previous to this, that obviously means we will need to break things up into components, right? And for example, yes, there may be a force acting on this block, but maybe at an angle. Well, then the only force that is being attributed to the work would be the horizontal force, because the block or the box is only moving in the horizontal direction. So as I just stated then, therefore, this may require multiplying the distance by a component force. as I said, just means taking the component so we get a direction that is the same direction as the motion. Number 2, so that's really the most important point here. One thing I didn't specify as I was going through that first page is that in US standard or US customary units, work has units of foot-pounds. So we go back here. Where I showed here foot-pounds on the left, even though I'm multiplying it by pounds times feet. Does that really matter? Not especially, but the standard is to show it as foot-pounds. So in US standard, work has units of foot-pounds. This is not to be confused with torque. Okay, these are two completely different things, and most of the time you will see that as pound-feet. So yes, essentially the same units, but they are two very different concepts. So before we can really move on, we need to really review some concepts here that you will have likely seen before, but these are really important for the remainder of this chapter. Also, it will help us, again, going forward in some of our other mechanical engineering courses. So with conservation of energy, the law of conservation of energy states that energy cannot be lost. Instead, it is converted from one form to another. These forms of energy include work, as we just talked about, which is, again, force times the distance. We have PE, which would be potential energy, and you'll often see me use capital E for short. We have KE, which you can probably assume then is kinetic energy. And we'll be looking at some others. Another one that might come to mind might be heat, often as a loss through mechanical motion. So one or two types of energy may initiate motion from one point to another and be converted to another form of energy in the process. And we're going to look at some examples. One you can imagine would be taking a ball. If you're holding a ball in your hand and you throw the ball upwards. Okay, so when it's released from your hands, it is released at a maximum velocity going upwards. So it has maximum kinetic energy at this point. As it travels upwards, it is losing that kinetic energy, but it's gaining potential energy. So yes, it is slowing down. Okay, and that would be, why is it slowing down? Of course, because of the acceleration due to gravity. But it's not that it's losing energy, it's just changing from one form to another. So instead of staying in kinetic energy, it's actually moving to potential energy. The higher you move an object vertically, the more potential energy it has, until it reaches a maximum potential energy at the top of its motion, at which point velocity is 0, and then it'll start coming back down. And as it starts coming back down, now it's losing potential energy and again gaining kinetic energy. So what we're going to do now is look at another form of energy. This energy would be work of a linear variable force, or another way of putting it would be simply spring energy. The required force to stretch or compress a spring is a force that varies linearly. This relationship can be expressed as follows. So work is equal to an average force. We'll discuss that a little bit more later. Average force times the distance. So it's not much different in its basic terminology. Work is just equal to a force, average. This would be force times the distance. However, the equation itself looks a little different. So work work of a spring here, would be equal to force, but because it's an average force, it's F over 2 times distance x. Now, in particular, for a spring, that force, F is equal to kx. This is what we're talking about, a linear variable force. It really means that as we increase that tension or compression, meaning that x value is changing from its base value, meaning it's uncompressed or it's not under tension. It's just sort of sitting, imagine a spring sitting on a table. So its x value is 0. As, say, we'll take this spring and we compress it. As we compress it, that x value increases. The force varies linearly with respect to that value x. The k is the constant, and that's really dependent on the spring itself. It's dependent on the material properties of the spring, say the number of loops of the coil, quite a number of factors. Typically in this textbook, and most of the time, you can just get that value from a manufacturer if you're looking to purchase a spring to use in a design. Again, for this textbook, we're just going to either give you that value or we'll find the value k, but there's really nothing special about it. So if we sub that value in for f is equal to kx, then what we have is kx over 2 times x. And then that gives us our work of a spring. So we'll, instead of using the term work, we'll use u like we did before, is equal to 1/2 kx squared. If we look at our units here, you can see that we still again have joules. Typically for a value of k, it would be given as newtons per meter. And we're multiplying that by a distance, but distance squared, so that would be meter squared. So of course that meter cancels out there, and we are left with our newton meters, which is equal to a joule, as expected. So just to show this, if that didn't quite make all that much sense, let's look at just a simple spring. And I'm going to show it as a simple diagram here. Okay. And what's going to happen is we want to apply a force. So the initial force here, F naught, that's equal to 0. So this is really the uncompressed spring, and this length is what we would call our free length. So free length when it is uncompressed. There's no force being applied to it. So now we'll look at it in its a second state. So we've now applied an actual force. So this spring is now going to be compressed due to a force being applied. So F1 has some value. Okay. So here's where we get our terms. This distance here, difference between free length and compressed length, this is our x value. We have an actual, so I said that on the left hand side, that's its free length. Now instead of being free length, it would be considered a compressed length. So again, the difference between the free length and compressed length is our value x. And now, when we are looking at the average force, remember average force right over here? Okay, I said that was F over 2, and that might not have made a whole lot of sense to start. And the reason for that, why is it F over 2? That's because our average force, if we look at this spring, would be F naught plus F1 divided by 2. Well, if F naught is 0, then our average force is just equal to F1 over 2, which is what we plug into our value for work. So hopefully that makes a little bit of sense to you there. And we will do some practice problems. Right now what I'm going to do for this video is just go through all of these different definitions, and then I will upload additional videos going through practice problems for each. And then the goal of this really of this chapter is to be able to solve problems very similar to what we solved in the last chapter. So now we're on to chapter 14. So the practice problems that we solved in chapter 13, we can now solve those with a whole other method now, and it actually gives us the opportunity to solve even additional type problems as well, compared to what we did last chapter. So let's move on. Spring energy, okay, we already did that. Potential energy then. So potential energy, imagine a weight being lowered from one level to another. It has potential to do work since it has a force acting through a distance. This object, therefore, is said to have potential energy. It has potential to do work, or convert its energy into another form, such as motion or heat, just as I talked about, say, with the ball, right? Normally it's measured from some sort of base, right? So, for example, if you're standing on the ground, that ground is considered your origin, your base, and so you have 0 potential energy. Now, when you jump up and you increase your distance off of that ground, you are increasing the potential energy that exists in you. Same with an object like a ball that you're throwing up, except in the example I gave, I'm throwing the ball up into the air from my hands, and so the hand is considered the base. So the equation for potential energy, so we'll call it PE for short, is equal to W. So now you see why we used U for work, because we are using large W. And what did I say that was for? That would be for weight. And weight is just equal to mg. So WH is equal to mgh. That's our equation for potential energy. And again, looking at our units, all units for energy need to be joules. So let's see if that works out. For mass, we have kilograms. For G, we have meters per second squared. And for H, we have meters. But remember that mg is kind of like F equals ma, and we get a force out of that. So that's newtons. So Newton meters again. So that does work. So again, when an object moves up against its weight, its potential energy increases. As it falls, it loses potential energy. So whether it's going up or down, it is changing potential energy. It really depends on what direction, right? It increases as it goes up versus decreasing when it goes down. As for kinetic energy, this can be expressed as follows. So Ke is equal to 1/2 m. Now you'll hear it as mv squared, but let's break that up as mv1 squared minus mv naught squared. So an initial and a final state. We have joules equal to kilograms times meters squared per second squared. And that would give us, again, our Newton meters, right? Because if we took the meters out here, technically we can show it like this. Kilograms times meters per second squared times meters. Same thing. So just like showed in the previous slide, that would be equal to our newtons. Okay. Okay. Now you might ask where we get this v1 squared minus v naught squared. You can either just take it for me that is correct, or you can actually look at how you would solve for that. So I'm just going to do that really quickly. You're not going to be asked to redo this, but it's good to sort of see how everything comes together, because it comes from equations of motion that we used in the first chapter in this course. So let's take just a real quick look at that. U is equal to, that's our work, equal to a force times a distance in general, right? Where F is equal to ma. So that means then that U is equal to mas. If we go back to our equations of motion, we remember that one of them is v1 squared equal to v naught squared plus 2as. Starting to look like something we might know here. So we're going to say, okay, therefore, if we were to rearrange this and solve for a instead, so I'm just rearranging this equation, v1 squared equals v naught squared plus 2as. I'm going to rearrange it for a. So a is equal to v1 squared minus v naught squared, and then I just divided through by that 2s. So I'm going to take this value and plug it into here, okay, for a. So the value a will be subbed in there. So u is equal to, I've got m. I'm going to plug in that value for a, v1 squared minus v naught squared over 2s. And I have an s left over. So of course those s values can then cancel out. So ultimately left with u equal to 1/2 m v1 squared minus v naught squared. Okay, so that's just the proof for the equation that I gave you at the top. Again, it's not something that you absolutely need to know, but I do like to try to tie up these loose ends so you can see how everything fits together. Okay, so conservation of energy, translational. The initial the initial energy equals the total final energy. Now, so this slide here in particular is not going to necessarily make a ton of sense to you right up front. I will come back to this when we do these exact problems. What I'm going to end up doing after I go through the rest of these slides, I will do a separate video just starting with the basics. Let's look at using each of those individual equations. Okay, what this does, this conservation of energy, and we're only going to be doing translational. So just as we did last chapter, I'm not going to get into rotational or planar motion. It is just rectilinear, so translational motion, up, down, left, right. But this is the idea that we take. This is sort of the concept that we use to solve the larger problems that involves multiple forms of energy, going from one form of energy to another form of energy. So no matter what form energy takes or changes to, all quantities must be accounted for. This method consists of considering only initial and final conditions. Always takes the general. It always going to take the general form. Activating energy equals resulting energy. And when I do these types of problems, I will tell you, this is what I want you to see. I just want you to write that equation out right there. Activating energy equals resulting energy, because it will remind you of what you have to do, how you solve these problems. So when we get to those types of problems, I will again go over that with you. I will remind you every single time, this is what I want to see. Energy is lost and it is gained. Okay, so it's lost in one form, but it's gained in another. Look for energy lost where it's lost and equate it to the energy gained by other objects in the system. So again, this might not make a ton of sense right now. I will bring the slide back up again when we get to these types of problems. So let's go over the last couple slides here for this chapter. A couple more of just simple, again, very simple equations, but we use these types of equations all through your courses at the college in the program. So first, power. Power takes into account the amount of time to do work and can be expressed as follows. So power is equal to, remember it says the amount of time to do work. So work over time. So work, remember, is a force times a distance, and time, of course, t. So this can also be shown as force times distance over time. And what's distance over time? That is force times a velocity. So a simple equation, easy to forget this one, but can be very helpful in some cases. Or we just show it as P is equal to work, which is U over T, where, of course, P is power, U is work, T is time, and the units for each, well, units for work is the units for work, joules, units for time is in seconds, and a joule per second, if you remember, would be a watt. Okay. So if we have watts, we also, that is the standard term for power in SI units. But when we're dealing in the US customary units, you're either dealing typically in horsepower. Okay, so if we want to be able to convert to horsepower, let's say power in horsepower is equal to F times S over 550 times T. And this is specifically if we have T in seconds. All right, or power, again, in horsepower is equal to force times time over 33,000, and this would be for T in minutes. Okay. All right, so that brings us to the last slide here, and this has to do with efficiency. We know, obviously, say for example, a motor is not 100% efficient. You input a certain amount of electrical energy, you get a certain amount of mechanical energy out of it. They're not equal. In fact, it can be quite low. In comparison, maybe 50%. So you have to put in twice the amount of electrical energy just to get what you want out in mechanical energy. So how do we express that? Well, we show it as follows. That's efficiency in percentage here is equal to power output over power input times 100. Okay. All right, so again, that's just basically stating what I said there. So for whatever percentage that you have for efficiency, so say you had a 50% efficient motor, you multiply that by the energy that is being input. So say electrical energy, as an example, say 100 watts times 50% would give us a power output of, what did I say, of 100 watts, so that'd only be 50 watts, right? So I will be giving you also examples for this one. So that's it for this video. I don't want to have super long videos. I really just wanted to get through the slides for this chapter. Again, there's not lots of slides, but I did introduce quite a number of new equations. So what I will be doing is working through practice problems for each of the different types of forms of energy. So we'll go through those first. And I will spend a little bit more time on the new concept, which would be springs. So some of you might not have seen that before. So we'll spend a bit of time on that. And once, hopefully, after one or two videos, if everybody's comfortable, then I will move on to the last section of this chapter, which would be bringing it all together. So doing larger problems using all of those equations. We'll start simple, and we'll work our way up. All right, so that's it for now. Have a good day.